Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on December 7th, 2025, about 3 days ago. It introduces a new rendering method called MeshSplatting that directly learns clean, connected, opaque triangle meshes from images, so the final result plugs straight into normal game and virtual reality engines without weird transparency issues or messy triangle soup. The paper is titled MeshSplatting, Differentiable Rendering with Opaque Meshes. And as we will see later, the visual quality and practical usability are both really impressive. Alright, Figure 1 shows what MeshSplatting delivers in practice across several scenes and interactions. The large left panel demonstrates high-definition game engine rendering that runs at hundreds of frames per second on a laptop, so performance stays real-time. The top middle panel adds a virtual object that physically collides with the reconstructed table, which highlights compatibility with standard physics engines. The top right panel turns the reconstruction into a walkable scene with a character exploring it. The bottom middle panel illustrates ray tracing with a reflective sphere, and the bottom right panel extracts a clean mesh of the table and centerpiece for direct reuse. Figure 2 contrasts how gradients flow in traditional triangle splatting versus mesh splatting. The left panel shows a triangle soup where each triangle owns its own vertices and attributes, so gradients stay local, and geometry between triangles never really coordinates. The right panel shows a shared vertex mesh, where neighboring triangles reference the same vertices. During training, gradients from multiple triangles accumulate at those shared vertices, which encourages smoother, more coherent surfaces across the whole mesh. Alright, Figure 3 walks through how the method turns a messy triangle soup into a clean, connected mesh. The top row shows the RGB appearance, while the bottom row shows the corresponding normal maps that reveal surface geometry. The left column starts from a noisy structure from Motion Point Cloud with semi-transparent, disconnected triangles. The middle column applies restricted Delaunay triangulation, which reconnects triangles but clearly introduces geometric and color artifacts. The right column presents the refined opaque mesh, where surfaces become smooth, details return, and normals look far more consistent across the table and background. Well, Figure 3 highlighted qualitative improvements, and Table 1 now backs that up with hard numbers. The left block lists methods and flags, whether they output meshes, colors, connectivity, and engine-ready assets. The middle columns report MIP-NERF 360 quality, where mesh splatting attains the best perceptual scores, with only about 3 million vertices. The right columns show tanks and temples, where mesh splatting again matches or beats competitors while using the fewest vertices and remaining directly game-ready. Alright, while Table 1 summarized metrics, Figure 5 shows how those numbers look visually. The full grid of images compares ground truth against mesh splatting, Milo, and triangle splatting across bicycle, truck, and train scenes. Mesh splatting panels appear crisper, especially in thin structures like the bicycle spokes. The red zoom insets along the bottom right of each panel highlight that mesh splatting preserves details and reduces blocky artifacts around the truck table legs and the train edges. So while Figure 5 focused on visual quality, Table 2 summarizes how fast and lightweight these methods are. The table lists training time, frames per second, and memory for each renderer on the MIP-NERF 360 dataset. Mesh splatting finishes training in about 48 minutes, which is roughly half the time of Milo. It also reaches around 220 frames per second in high definition and 190 in full high definition, while fitting into about 100 megabytes, so it stays both real-time and very compact. So while Table 2 emphasized speed and compactness, Figure 13 turns to failure cases. The entire figure illustrates how the method struggles in cluttered backgrounds and on transparent objects. The left panel shows a forest scene where the distant foliage inside the red boxes becomes mushy and incomplete because the underlying point cloud there is too sparse. The right panel shows an indoor scene where the transparent bottle in the red insets becomes blocky and distorted, since opaque triangles cannot capture true transparency. Mesh splatting shows that you can train directly from images to a compact, connected, fully opaque triangle mesh that drops straight into standard game and virtual reality engines, while staying fast and lightweight. The method narrows the gap between neural rendering research and practical, interactive graphics. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.